One of the great features of the Task Parallel library is that it can weave together hundreds or thousands of tasks in complex patterns. To connect tasks together, you have two dimensions to work with. You can create a hierarchical layering of tasks and have parent tasks break down complex work into asynchronous units of work that can run in parallel. And the other dimension is sequential. Sometimes a task consists of a discrete number of steps that have to be performed in a specific order. For this scenario, you can link tasks together into so-called continuations, sequences of tasks that execute one after another. You can freely mix and match from both dimensions. A parent task can assign work to 3 child tasks, wait until they complete, and then move on to the next task in a continuation sequence. In this lecture, we are going to look at the second dimension, task continuations. You can visualize task continuations like this. So in this diagram, I have 3 tasks, and each subsequent task is going to run when the previous task completes. The 3 tasks run sequentially, one after another. You might think this is all a bit silly. Sequential tasks cannot be run in parallel, so there's no point assigning them to different threads. And the code is functionally the same as simply putting everything in a single method. But the reason continuations exist is because most parallel work consists of 3 discrete steps. 1. Split a problem into many units of work that can execute in parallel. 2. Execute the units of work. 3. Assemble the finished work into a result. There's even a name for this process: MapReduce. The word map refers to breaking up a problem into units of work, and the word reduce refers to aggregating the finished work back into a result. You can easily implement this process with tasks by creating a 3-step continuation: the map step, the execution step, and the reduce step. The execution step will be a parent task with many child tasks to execute the work. And because it's a parent task, it will not continue until all child tasks have completed their work. When the final task executes, it knows for a fact that all child tasks in step 2 have completed. So now it can safely collect all the results and aggregate them together. Your calling code can simply call the result property of the final task in the continuation to collect the result. Let's build a demo application that combines continuations and child tasks to perform some kind of work. I'll use the word reversing code from the previous lecture and build upon that. If we look at the word reversing problem, then there are essentially 3 steps to it. 1. Split the sentence into words. 2. Reverse each word with child tasks. 3. assemble the reversed words back into a sentence. In the previous lecture, I only talked about parent and child tasks, because we didn't cover continuations yet. So I split the sentence in the parent task and assembled the results in the main program method. Now let's clean up the code. I will create 3 discrete tasks that perform each step of the MapReduce process. So here is my modified word reverser that I have called Better Word Reverser. At the top here is again the string reverser method called reverseString. This method is exactly the same as in the previous lecture. Even the 1-second sleep is still there. Then we get down to business. The MapReduce process has 3 discrete steps, which I have called map, process, and reduce. Let's start with map. This is a very simple method that expects a string, which is the sentence, and it returns a string array of all the words in the sentence. The body of the method is simply a call to split to create the list of words. Then comes the process method. You can see that the method receives an array of words in the first argument, and it returns the modified array of words with the characters in each word reversed. It accomplishes this by starting a long-running child task for each word. Each child task picks up a single word, reverses it, and puts it back in the array. The process task then returns the word array as a result. The task will complete only when all of the child tasks have completed. So by the time this result becomes available, all words will already have been reversed. Finally, there is the reduce method. It accepts an array of words in the first argument and returns the assembled sentence. The method body uses a string builder to append all the words together, delimited by spaces. And now for the cool stuff. Check out the main program method here that chains these methods together. These 3 lines create the complete process. I start by creating a task to call the map method. The task creates a word list, so I use the generic task with a string array type parameter. The lambda expression simply calls map with the hard-coded sentence and returns the resulting word list. On the next line, I continue with the continue with method. This sets up a continuation and adds another task to the sequence. I use the generic method with a string array type parameter because the process step returns a string array. The lambda expression calls the process method, feeds in the results of the first task in the sequence, and returns the results, which will be the word list with all words reversed. I end the continuation with the third line. Again, there's a continue with method, this time with a generic string type parameter, because the reduce method returns a string. The lambda expression calls the reduce method, feeds in the results of the previous step, and returns the result, which will be a new sentence containing all the reversed words. Notice that each continuation lambda expression receives an argument t, which is the task of the previous step in the sequence. With this argument, I can access the results of the previous task and use them for the next operation in the continuation. To get at the results of this entire chain of tasks, all I need to do is store the result of all the continuations in a local variable called task. This variable will refer to the final task in the sequence, and therefore, when I access its result property, I get the assembled string with all the words reversed. Let me run the program to prove that everything is working. Here we go. And again, there you have it. A 1-second delay, and then the sentence with all the words reversed. So, what have we learned in this lecture? Tasks can be connected hierarchically and sequentially. Sequentially connected tasks are called continuations. Each task in the continuation starts after the previous task in the sequence has completed. The lambda expression in each continuation can access the results of the previous task. Continuations are perfect for setting up multi-threaded MapReduce processes in C#.